So we've already started talking about positive and negative linear relationships, started to talk about positive and negative correlations, looking at the two variables and looking to see maybe how they may be related. And so now we're going to talk about the strength and direction of the linear relationship between two quantitative variables. So we have that it's from -1 to 1, where -1 is a strong negative correlation and +1 is a strong positive correlation. And correlations close to 0 are fairly weak. Okay, so this is positive, this is negative. We really say no correlation at this point. So properties of correlation. Correlation can only be measured between two quantitative variables. If r is greater than 0, the two variables are positively associated, so slope of points is positive. If the correlation, right, so r is less than 0, they're negative. Correlation is always between -1 and 1 inclusive. So values of r that are close to 0 indicate a very weak linear relationship. The values of r that are close to 1, -1 indicate a very strong linear relationship. And values of r that are equal to 1 or -1 are a perfect linear relationship. So let's take a look at some examples with our example 1. Consider the following scatter plots and their corresponding correlation values. Classify the strength and direction of the linear relationship between the two variables in each scatter plot. So if I circle, right, it's not a perfect straight line, right? But it's very, very strong. And you notice they give us an R, right, a correlation of 0.94, which is fairly close to 1. So we would say this is a strong positive. You could even say linear correlation. Now let's look at B, right? So if we look at B, it's showing there's -1, but you look and there's not very much going on here, right? It's fairly close to 0. It almost looks sort of just a general scatter plot. So we would say this is very weak, right? Weak correlation. We would almost say this is almost none, right? It's not 0, so there is some type, but it's very weak correlation here. And we could say weak correlation, right? And we could say negative, since we see that R is negative. Now, if we look at C, we notice again the correlation, right, is -0.88, which is fairly close to -1. So we could say a strong negative linear correlation. And my last one, right, the D, you can definitely see there is more of a positive linear correlation, but we could say maybe a weaker, right? So it's a weaker positive linear correlation. So one of the things to note as well when it says, if we look at all of these, the sign of the correlation doesn't really matter, right? So if I had a correlation of 0.94 or -0.94, and we said which one is stronger, they are actually exactly the same. One just identifies negative, one's identify as positive, but the strength of their relationship would be the same since they're exactly the same correlation. So the sign doesn't really matter. The sign just tells you whether it's a positive or negative correlation. The number itself, whether, which one's closer to 1 or -1, that sort of determines which one's stronger. So let's look at our first example. It says, find and interpret the correlation for the education and income data set. So we've actually seen this in section 10.1. So you may have this data already entered into your calculator. But if we look at it again, years of education, this is our independent variable, or X, and Y is our dependent variable. And we saw in the previous section that there is a positive linear, we don't know if it's a correlation, but it looks like there's some correlation between these. So we're actually going to find the correlation in this case and then interpret it. So if I want to do this, you may or may not have already have your diagnostics turned on, but we want to make sure our diagnostic is on. So we would hit our second button. We're going to hit catalog, And we're going then to hit x to the negative 1 since it says a D there because we want the diagnostic on. We're going to scroll all the way down till we find diagnostic on, hit enter, and you should be good. Again, you may have already done this and it may already be on your calculator, but if not, just make sure you do this. And as long as you don't reset your calculator, you should be good to go. So we're then going to enter this data into our calculator. So I'll hit my stat button, I'll hit edit. I already have this data already in since we've worked with it in a previous section. So if you want, you can pause the video, go through and enter this data. So X is going to be L1 and Y is going to be L2. All right, so once you've entered this, you'll hit your stat button. You'll go over to calc and you're going to go down to the number 4, linear regression. So L1 is X, L2 is Y. We're going to then hit calculate. So the first part here, this is from our last section with our linear regression. R squared and R is what's in this section. R squared we'll talk about in the next little example, but it's our coefficient of determination. And R is our correlation. So if I write down what R is, right? So R is equal to 0.974. So if we wanted to interpret this, right, we would say there is a strong positive linear correlation between, and then we're going to list the variables out, between years of education and annual income. So we saw from the scatter plot, right, that there was a linear, right, trend, linear relationship, and now we can see that there is a strong positive linear correlation between these two variables. All right, so our last little bit is our coefficient of determination. The coefficient of determination is the percent of the total variation in the y variable that is explained by using the variable x in the regression. Again, note, r squared is going to be between 0 and 1. And if you think, right, if you had, why this works, right, less than or equal to r less than or equal to 1. If you square both sides, basic, you'll end up with, there's not going to be a negative value side. So it could be 0, anywhere between 1. The coefficient of determination is commonly used to describe the success of the regression in explaining the response variable y. So we want to find and interpret the coefficient of determination for the education and an income data set on the previous page, right? So it's actually on the same page, but we had r, right, was 0.974. R squared is literally just, you're going to square, right? If you square 0.974, now it is on the calculator, so you can write that down. But if you were just given r, if you just square what r is, you would end up with what r squared is. So here is my coefficient of determination. And what this means is roughly, so 94.9% of the variability in annual income, right? So my dependent variable, my y variable, is explained by including, and it's whatever your x variable is, your independent variable, by including number of years of education in the model. And so the higher your coefficient of determination is, sort of the better model it is. So this is an excellent model. So if you had something around, 50%, 25%, not a really great model, and you probably would see there's really not a great strong correlation also with that. So that is my coefficient of determination. You can really find your linear regression, coefficient of determination, and your correlation all using that linear regression, and then just use them in different aspects by interpreting it and looking at what those values mean.